Okay, welcome back. Our next speaker is Stipe Kabic, who's machine learning engineer at Atomic Intelligence, and the name of his talk is The Nuts and Bolts of Music Source Separation. The topic of the talk will be in-depth overview of the machine learning techniques used for audio data modeling, and the focus will be on applications in the task of audio source separation. So welcome, Stipe, and Mike is yours.
Hi everyone. Hi from our offices in Zagreb, which I am very much so looking forward to leaving for tonight. So let us start with the presentation. I assume I do this and upload. There was an opportunity for me to test StreamYard with you, but I missed it due to a colleague visiting our offices. So this is the first time I'm using this. Okay. Slides. Okay, so you can see the slides now. So the title of this talk is The Nuts and Bolts of Music Source Separation. The reason for the name is because it's intended to be a talk for practitioners, for people who are also working with audio data or are practitioners in other fields of machine learning and are looking to maybe try out some new projects and want to know what are the differences when you're working with audio data. And so what we will be talking about today is first we'll have a small introduction to the problem of music source separation, but we won't dwell on it too much because the idea is for it to just be a representation of working with audio data using machine learning. The second part will be looking at some state-of-the-art modeling approaches, which mostly are similar for music source separation, as well as many other tasks, such as working with speech and other problems in audio data. Then we will continue with a couple of practical tips on little things that were proved to be very useful to our team and that we would like to share with everyone else. And after that, we will go on with some research directions and ideas and some of the new things we are working on currently. Okay, so let us start with the problem of music source separation. So this is a very hard problem, and why? Well, one thing is the songs are created by recording a couple of different instruments and then mixing them together, and what your model sees is only the mix, and it has to learn how to separate many different instruments from just this one single representation, which is much more difficult than most other problems that exist in machine learning. Usually when you get an image, the thing you're trying to classify or detect is in the image. When you're working with text data, you have to detect entities inside the text or something like that. Here you have to actually generate entire audio files from just this one input mixture. The other thing that is very difficult with audio data is the fact that there is a lot of it. So for 1 second of audio data, there is actually, usually with music, 44,000 samples. And songs usually last from anywhere from 3 to 5 or 6 minutes. So it is a very large amount of data. Data sets can be in size of terabytes, and it's very difficult to work with such data. Also, there is a problem of not having large pre-trained models and large data sets to use for transfer learning and such things. And another difficulty is annotation as well. Like, it's very difficult to annotate audio data. You have to listen to it. Music source separation is also very hard unless you have the original stems. So what that means is that there is a multidisciplinary approach required for solving this problem. So most deep learning practitioners, they work either with images, with computer vision, or with text data, NLP. And we will see that audio, depending on how you process it, can be represented in ways that are very similar either to audio or to either to images or to sequences such as text. But in order to get to those representations, there is a lot of underlying mathematics and signal processing techniques that can be used to get this, and there is also a requirement for people who know this sort of theory and understanding. It's not so easy as just plugging in the data and running it through a model. And also there is a lot of already existing knowledge of people who work with audio, with music, with effects and such things, which can also be very useful in working together with the models. So what are the approaches to modeling audio data? Well, the most used tool is the Fourier transform, which generates spectrograms. So you take your audio, you take small windows of it, and you apply a Fourier transform to get frequencies. And you stack those together and you get a spectrogram, which is something like an image, which is why computer vision practitioners can be very useful in working with audio data, because these spectrograms, well, they're pretty much our images, and you can work with them using standard architectures that you use in computer vision. Um, However, so it's not as simple as that. So for example, here you have a spectrogram and you're trying to separate an instrument. So the way it works is you provide a mask. This is very similar to like working with segmentation in computer vision, where you're trying to segment an image into foreground or background, something like that. But if you use only like binary masks, which are used in computer vision, you get a chunky output like the one on the right, which means you have to actually use continuous masks and uh, different modeling techniques which get a bit more complex. Uh, Another way you can work with this is working directly with waveform models. So you take in just the original audio, which is the way computers usually represent it, and you feed that into a model. However, this is also a very difficult task because the original representation tends to be very long, as I said already, 44,000 samples for just 1 second. So once again, you have to do some pre-processing steps, some mathematical modeling in order to get a nicer representation of your waveform, which can then be provided to your models. And as usual in machine learning, the best approaches tend to combine these two avenues and work on both the spectrograms, which is a vision approach, and on the sequences from waveforms, where some techniques similar to NLP and other areas can be used. And this is also what we are currently working on, some solutions that combine both of the approaches. So what are some practical tips that we have found useful? Where one thing is really understanding audio data. So images, text, this is pretty natural to humans. Like most tasks that deep learning is used for, humans can also do in those fields pretty easily. Classifying things on images, understanding text and answering questions. This is not very difficult for us, and it's quite understandable. So you can pretty much take the data, throw it into a model, and get to work. However, with audio, it's a bit more difficult. There are a lot of nuances with the instruments, with harmonics, with the way they sound, overlapping frequencies, a lot of that, and there's a lot of music theory, that there is this entire area of research which needs to be understood to a point to be able to better work with audio data. So it's also important to listen to a lot of the audio you're working with to make sure the things you are doing to it mathematically or with models actually make sense musically, or if you work with speech, to that it preserves the structures in speech that are important to process it further. So another thing is using state-of-the-art methods in deep learning, because often because audio data is quite difficult to work with and because you have to provide custom models, a lot of the research ends up being super focused on that, but then it forgets to use some standard tricks that everyone working in computer vision or NLP uses and gets good results with it. And you see papers in audio research where people just tend to use techniques that are a couple of years old and not use some of the best approaches because they don't have time to figure out both the state of the art in deep learning, plus all the signal processing required to work with audio, plus design their custom neural networks to do the separation. So here we once again see the requirement for a team of people with different approaches and different backgrounds to get together and solve this problem. And another thing that we have recently developed and are starting to use is the MobileNet architecture, which is in my opinion, maybe the most underrated machine learning model that exists. It's never the best model for any given problem, and because of that, it doesn't get reported, as increasing the result on some standard problem by 1%. But what this model does is it works nearly as good as much larger models and can be saved in a much smaller memory space and trained much faster and used for much faster inference on smaller devices and even on CPU, which makes things much easier because of the nature of audio data and how the data is so large. Our larger models tend to take 2 to 3 days to train, which makes it quite difficult, to run experiments. You get an idea, you want to try it out. If it works, you need like 2 trainings, which is basically a week on a single GPU. So the MobileNet is excellent because it allows us to test out some of our new ideas in a couple of hours, see if it works or it doesn't, and get on with it. Um, okay, so the last part will be a couple of directions we think this area is going and what can be done to get better models for both music source separation as well as other audio problems. So one thing is basically picking up on all the new improvements from other areas where deep learning is used. For example, on the left we have this graph which shows the best current computer vision models pre-trained on ImageNet. And this interesting thing is that the ResNet, which is already a bit outdated and doesn't get the best results, is the most advanced computer vision architecture which has been used in the problem of music source separation, which we are working on, and nobody had the time or remembered to apply some of the more advanced approaches. There are also a lot of smaller techniques that can be used to improve the training of these models, and a lot of these things have never been tried out in audio. And on the right, we see the good old transformer model, which has taken over NLP, computer vision, and pretty much everything that can be modeled with deep learning. And it has been used in audio recently with the OpenAI Whisper. This exact architecture, the simplest transformer from the original paper, was used to get a great speech recognition model, but it has not, for example, been used successfully yet in music source separation or something like that. So we are currently working on some approaches which will apply these sorts of models. Another thing is also looking back at the fundamentals. So the ways of representing audio, the way you calculate the spectrograms, the way you do the Fourier transform. This is an entire field of digital signal processing, which there are books written just about, doing this one thing. And usually in deep learning, people take the basic package the simplest one that can do the thing. They do the thing, get the spectrogram, work with it without really thinking what this representation is and if it is actually the best way you can model audio data. So we are also looking to get together with some mathematical background and try to apply some techniques from those areas as a pre-processing step for our machine learning models. And so that will pretty much be it. The end of all of this should be creating a novel music source separation approach which will combine the best existing approaches as well as modern techniques of deep learning and the fundamental mathematics to get something that works better than what we currently have. And this is something we are continuing to work on, and we hope others will also join. So that would pretty much be it.